Let's start learning Chapter 9, Linear Momentum. So we have learned a conserved quantity, energy, and we found out that conservation of energy can help us simplify a lot of problems. So we are going to learn another conserved quantity, momentum. And not surprise, momentum can help us simplify a lot of other problems too. Now the definition of momentum is very simple. Momentum is defined as mass times velocity. And if you remember, velocity is vector, mass is scalar. So momentum is mass times velocity, and the momentum is going to be a vector, which means momentum has a direction, and the direction of momentum is the same as the direction of the velocity. Now, if we go back to Newton's second law, now maybe right by now you are more familiar with F equals ma, but actually when we were discussing Newton's second law, we mentioned the more rigorous definition of Newton's second law should be force equals change of momentum over time. Differential of momentum over time give you force. What is the change of momentum for the cart? Now, of course, we need to define a positive direction for this, because let's say this is positive. So the momentum of the cart before it bumps into the wall should be 20, actually it's negative 20 kilogram times meter per second. And then after the bouncing off the wall, its momentum is 10. And the change of momentum, of course, is final momentum subtract initial momentum should be 30. So this is a concept, the change of momentum. Now, we have learned change of energy, which is a work. So if you recall, work is force times displacement times cosine theta. Force times displacement give you work, change of energy. Now we want to explore what quantity give you change of momentum. Now let's try to explore the special case of free fall. So you have something falling down. We use a kinematic equation, final velocity equals initial velocity plus at, and your a is negative g in this case, because you choose up to be positive. Okay, so change of momentum is final momentum subtract the initial momentum. Final momentum is mass times final velocity. Initial momentum is mass times initial velocity. Now, final velocity subtract initial velocity equals g times t. So you have change of momentum equals force times delta t. Now, let's check the dimension. So we say whenever you have an equation, the dimension of left-hand side should equal to the dimension of right-hand side. Now let's check the dimension by checking the unit. Left-hand side is kilogram times meter per second. Okay. And the right-hand side unit is Newton times second. But you need to go back to the SI unit of Newton. 1 Newton is 1 kilogram meter per second square, if you remember. Now you multiply this 1 Newton by a second, so it will give you 1 kilogram meter per second. So you see the left hand side, the unit equals to the right hand side. So dimension is consistent. And this gives us a very important relation. Change of momentum equals force times time interval. And which is also consistent with Newton's second law, right? F equals change of momentum over t. So if you move this delta t to the left hand side, you have change of momentum equals F times delta t. So let's try to enhance our understanding of momentum by looking at this conceptual problem. Now we have two ice boats racing on a frictionless lake. One, the mass is m, the other one mass is 2m. Now we have wind exert the same force on both boats. And then both boats start from rest. Both travel same distance to finish line. So both boats travel same distance, same force, same distance. We're going to ask which one can cross finish line with more kinetic energy. Now pause this video, think it about 2 minutes until you get the answer. Now welcome back. Now we want to answer which one crossed the finish line with more kinetic energy. The answer should be they should have the same kinetic energy. And why is that? Because you have the same force, they travel the same distance. So the work done by the wind on both boats are the same. And when the work are the same, you have work energy theorem. Change of kinetic energy equals to the work done by the wind. And the work done by the wind are the same, so they have the same kinetic energy. Now, which one has more momentum? Because they have the same kinetic energy, which you have 2m1 v1 squared equals 1/2 m2 v2 squared. So, which means the velocity of boat 1 and boat 2 are different. Let's say boat 1 is mass m and boat 2 is 2m. So you have mv1 squared equals 2mv2 squared. Give you v1 equals square root 2 v2. So the boat m1 has velocity square root 2 times velocity of boat 2. So you see the momentum of boat 1, p1 is m square root 2 v2. Momentum on second boat is 2m v2. Now apparently boat 2 would have higher momentum. Okay, almost the same scenario. Except this time you have two boats start from rest. Both travel same amount of time. So everything stays the same except this time we ask those two boats to travel same amount of time. And then we ask which one has more kinetic energy and which one has more